Welcome back, sports fans, and we're finishing up 3.3, measures of variation. This is the second part of your notes, so you should have those pre-printed notes out in front of you. And what we're talking about today is to be able to describe data by calculating the coefficient of variation and the range rule of thumb. So we've already been talking about the standard of deviation and how certain data is distributed. We're going to go on with the coefficient of variation. We were using the standard deviation if you have the data of two sets in the same unit. So you can compare them with standard deviation if they have the same units of measurement, like temperatures in Arizona and temperatures in Boston. Coefficient of variation it's called, because certain units are smaller than other units, so standard deviations, it's all relative. So such as the number of sales made per person and the commission, that would have to be, when you have two different units of measure, you have to use the coefficient of variation. So don't you want to know what it is? Here's the coefficient of variation. It's a statistic that allows one to compare standard deviation when the units are different. The coefficient of variation is noted by C-var. It's the standard deviation divided by the mean. C-var sounds like something a pirate would say, but no, it means coefficient of variation. So you just take the standard deviation, you divide it by the mean, and you express the result as a percentage. Your book kind of is mathematically fudging it a bit. So I like to put it like this. Here's the standard deviation, little s, over the mean, if you notice it's got a bar on top. And I multiply by 100 and put a percentage symbol at the end. But if you know decimal, if you can change a decimal to percent, that's all you do. So if it's a population, they use the other little symbols. This little fishy is for standard deviation and the mu for the mean. Pretty easy. Standard deviation divided by the mean. That's all it is. So here we go. The mean of the number of sales of cars was 87. The mean of the commission is 5,225. They give the standard deviation. Here it's 5, here it's 773. Compare the variations. All we're going to do is take the standard deviation 5 and divide it by the mean. So sales, we're going to take standard deviation over the mean. It's going to be 5 over 87. That's going to give us the decimal of 0.057. They say to multiply by 100, but you guys are sharp. All you do is move the decimal 2 spaces to the right and put a percent at the end. So that's 5.7%. Commission, 773 divided by 5,225. Again, 773 was the standard deviation divided by the mean. Bada boom, bada bing. You get 0.148. That's 14.8%. So then you can compare these. Which one's more variable? The one that is higher is the one that is more variable. And you can see the commissions have a higher C-var, coefficient of variation. Since the coefficient of variation is larger for the commissions, the data are more variable than the sales. So that's how you can tell two sets that are more variable. So let's take a look at the next one. Number of pages of women's fitness magazines is 132, variance of 23. The mean for the number of ads of samples women, number of ads, is 182 with a variance of 62. Compare the variations. And you say, wait a minute, they didn't give a standard deviation. But it's just the square root of the variance. So all I have to do is take the square root of the variance. Remember, that is standard deviation. So for the pages, we'll take square root of 23 over 132. We'll get 0.036 or 36 thousandths. Move the decimal 2 spaces to the right. That's 3.6%. The ads, we will take square root of 62 divided by 182. And that's going to give us a grand total of 0.043, which is 4.3%. This guy's higher. 4.3% is bigger than 3.6%. So the number of ads is more variable than the number of pages, since the coefficient of variation is larger for the ads. That's all there is to it. Okay, we're going to head into range rule of thumb. This is a quick and easy way to compute standard deviation. So it is just an approximation. So a rough estimate of the standard deviation can be given with the formula. And notice your book a lot of times uses equal signs. I use the squigglies because that means approximately equal to. There it is. Range over 4. So standard deviation is approximately the range divided by 4. So if I'm given this data set, to find the approximation of the standard deviation, I have to first find the range. The range is the high minus the low. So 13 minus 5 is 8. So standard deviation is approximately 8 divided by 4. That's an approximation for the standard deviation, which is 2. Just a quick and easy way to compute standard deviation without doing all the sums and the x squareds and all that jazz. So caution, range rule of thumb is only an approximation and should be used when the data is unimodal, one mode, and roughly symmetric. Alrighty, the mean for the previous data set is 9.3. Use it to estimate the largest and smallest data value. Range rule of thumb can be used to estimate the largest and smallest value of the data set. The smallest value will be about 2 standard deviations below the mean, and the largest data value 2 standard deviations above the mean. So if I'm trying to just approximate this, I would take the mean, that's this symbol, plus or minus 2 times my standard deviation, which in the last slide we saw was 2. So we're going to take the mean, which is 9.3, we're going to subtract 2 times 2, and we're going to add 2 times 2. So this will give us our smallest data value, which it says is 5.3. That's pretty close, because the smallest data value was actually 5. If we do the largest one, we'll have 9.3 plus 2 times 2. That's going to give us 13.3. A little bit higher, but that's okay. So that's all that is. So you can use that to approximate the high and the low for your data value. Notice that the actual smallest data was 5. Remember, this is a rough approximation. Usually almost all data falls within 2 standard deviations of the mean. Alright, following theorem specifies the proportion of the spread in terms of the standard deviation. It's called Chebyshev's theorem. The proportion of values from a data set will fall within k standard deviations. So this is the number of standard deviations, not the standard deviation itself, where k is a number greater than 1. K is not necessarily an integer. So when you're looking at this, you see this name Chebyshev's. People get that mistaken with Chevy Chase. Chevy Chase, totally different guy than Chebyshev. See, Chevy Chase, Chebyshev's. Chevy Chase starred in the vacation movies with the family, you know, and also with the Three Amigos. Here he's dressed as a mariachi asking, do you have anything besides Mexican food? I thought he was hilarious, by the way. But this is something totally different. So Chebyshev's theorem is this thing about the proportion of values of a data set. So when I look at this, here's how it works. You've got it within k standard deviations of the mean and will be at least 1 minus 1 over k squared. So if we substitute k equal 2 into the expression, we get the following result. At least 1 minus 1 over 2 squared. Okay, if we simplify that, we get 1 minus a fourth equals 3/4. So that means that 3/4 or 75% of the data values fall within 2 standard deviations. So you're seeing how much data falls within a number of standard deviations from your mean. If we substitute into 3, so we'll have 3, we put that in there, 1 minus 1 over 3 squared. Remember, you square the 3, so it's 1 minus 1/9 or 8/9. That's 88.9% of the data values will fall within 3 standard deviations of the mean of the data set. Thing works. Here's an example of where you would use it. The mean price of houses in a certain neighborhood is 50 grand, and the standard deviation is 10,000. Find the price range for which at least 75% of the houses will sell. So if we look at this, since 75% is the same as 3/4, we use Chebyshev's theorem and solve 1 minus 1 over k squared equals 3/4. We want to know how 75% of the houses. So what we're going to do is we're going to solve for k there. So we get the opposite of 1 over k squared equals negative 1/4. And using cross products, you can do negative 1 times 4, k times negative 1. You could also flip both of them. That's another way you can do proportions. So you get negative 4 equals the opposite of k squared. So k squared equals 4. Take the square root, you get k equal 2. Therefore, 75% of all the data values will fall within 2 standard deviations, which we kind of already knew, right? Should fall within 2 standard deviations of the mean. Minimum value, you take the mean minus 2 times the standard deviation, which in this case the standard deviation is 10,000. So mean minus 2 standard deviations is going to be 50,000 minus 2 times 10,000, which is going to be 50,000 minus 20,000, or $30,000. So that's the low price for 75% of the houses to sell. Find the maximum. Instead of minusing 2 standard deviations, we're going to add 2 standard deviations. So we'll have 50,000 plus 20,000, which gives us 70,000. Therefore, at least 75% of all homes sold will have a price range from 30,000 to 70,000. So that's where 75% of the houses will sell. And that's Chebyshev's. Chebyshev's theorem can also be used to find the minimum percentage of data values that will fall within any 2 given data values. This procedure is shown here. A survey of local companies found that the mean amount of travel allowance for executives was 25 cents a mile. The standard deviation was 2 cents a mile. Using Chebyshev's theorem, find the minimum percentage of data values that will fall between 20 cents and 30 cents. So your first step is to subtract the mean from the larger value, because remember, it's the mean minus a number times the standard deviations to figure this out. So you get a nickel. 30 cents minus 25 cents. Next, divide the difference by the standard deviation to get the K. So the difference was a nickel divided by 2 cents, which is going to be 2.5. That's the number of standard deviations. Remember, K does not have to be an integer. Step 3, use Chebyshev's theorem to find the percentage. So the percentage of values, we're going to have 1 minus 1 over K squared. So it's going to be 1 minus 1 over 2.5 quantity squared, 0.84. Should have been 1 over 6.25. Sorry about that. There should be a 1 over here. So you get 0.84 and you get 84%. Therefore, at least 84% of the data values fall between 20 and 30 cents. All right, empirical rule. Now we're going to hit this just to introduce this to you today, but it will come up again and again later on. Chebyshev's theorem applies to any distribution regardless of its shape. However, when a distribution is bell-shaped, or what is called normal, the following statements which make up the empirical rule are true. This is also how they test to see if your distribution is normal or not. Approximately 68% of the data values fall within 1 standard deviation of the mean, 95 within 2, and 99.7 within 3 standard deviations. So let's look at how this chart looks. So here is our data value. You can see the bell shape here. What this means is the mean. X with the bar, that's the mean. This right here is the mean plus 1 standard deviation. So right between these two values, 68% of the data is going to lie. Between 2 standard deviations, 2 to the left and 2 to the right of the mean, you're going to have 95%. And 3 standard deviations, almost all of your data should go between 3 standard deviations, 99.7. All right. Suppose that the scores on a national achievement have a mean of 480 and a standard deviation of 90. If these scores are normally distributed, then approximately 68% of the data fall between blank and blank. So this is what we're figuring out. Well, you know, if 68%, that's 1 standard deviation to the right and to the left of the mean. So we're going to take the mean minus 1 standard deviation, which is 480 minus 90, you get 390. The mean plus 1 standard deviation, the mean was 480, the standard deviation is 90, we add those, we get 570. So it's going to fall between 390 and 570. Approximately 95 will fall between 2 standard deviations, so we're going to do the same thing, except we're going to multiply the 90 by 2 on both of those. So mean minus 2 standard deviations is going to be 300, plus 2 standard deviations is going to be 660, bada boom, bada bing. With 99.7%, it's going to be, instead of 2 times 90, 3 times 90, because it's going to be the mean minus 3 standard deviations and the mean plus 3 standard deviation. So it's going to fall between 210 and 750. Okay, I believe that is it. I hope you have a great day, and I will see you later. Go Cards!